team, the formidable team we have in STU. That is our faculty members and students of Sunyani University. We take the special honor to also welcome our team from SUNY Polytechnic in the USA, led by the very noble professor, a man who inspired us and motivated us to excel at Black English, Professor Wole Soboyejo. Let us give him a round of applause. Today's public lecture is themed Next Frontiers for Artificial Intelligence, Robotics and Advanced Manufacturing. I am here to tell you today that you have not wasted a second of your precious time to be in this module. Because today we are not just giving you new technology, we are bringing AI to your doorstep, and we are making sure that you get all the technology outside the country. You get well abreast with it. Students, today you get the opportunity to meet with other knowledgeable students from around the globe, particularly from USA. And we thank God for this opportunity. Without wasting time, I will invite our very own Dr. Isaac here to give us the introduction of the main speaker.
Thank you very much, Madam MC. The visit of Sunyani University, our invited guest from the SUNY Polytechnic, led by the President, students, ladies and gentlemen, all protocols observed. I feel honored to be called upon to introduce a very important personality in our midst. In fact, the main speaker this afternoon. This honorable man received his PhD in mechanical engineering from the King's College, London in 1985 and the PhD in material science from Prof University in 1988. He then moved to the US as a research assistant, as a research scientist at the McDonnell Douglas Research Lab, 1988 to 1992. Since then, he has been an assistant to associate professor at the Ohio State University, 1992 to 1999. A visiting Martin Luther King Associate Professor at MIT, 1997 to 1998, and a professor of mechanical and aerospace engineering at Princeton University, 1999 to 2015. He has also served as a president, a provost of the African University of Science and Technology, 2012 to 2014. Then I am Gordon Dean of Engineering, 2016 to 2018, Provost 2018 to 2023, and interim President 2023-2024 at the Worcester Polytechnic Institute, WPI. In 2023, he was appointed as the 7th President of the State University of New York Polytechnic Institute, SUNY Polytechnic. He is the author of 5 books and more than 400 papers in peer-reviewed journal papers. He is a member of U.S. National Academy of Engineering, a fellow of the World Academy of Science, the African Academy of Science, the Nigerian Academy of Science, the Nigerian Academy of Engineering, the American Society of Mechanical Engineers, the American Institute for Medical and Biological Engineering, and the Material Society of Nigeria. Wow! Ladies and gentlemen, with rich profile, please, with a resounding round of applause, please help me welcome Professor Dr. Wole Soboyejo. Audience, your professor, and professor, your audience. Ready to listen to you.
Thank you very much. Okay. So first of all, thank you very much for that very kind introduction. I truly appreciate to be here today. I'll be sharing you a few ideas. And before we start the next slide, I want to give you some opportunity to appreciate Professor for his leadership and his friendship. Him and I, through the lockdown that was facilitated by Tabir, have been cultivating a good relationship, and we're truly delighted to be here. Also, I want to use this opportunity to thank Professor Sam who's been a good friend to us, and my colleagues in the United States colleagues here for this occasion. Now, I saw a few people at the back, and there's a reason why I do this. So in many ways, what I'm going to describe to you at the activity is somebody who is trying to do science and engineering. But I'm supported by a network of people that have really fantastic. So basically, as a scientist, I've had an opportunity to work with presidents, I've had an opportunity to work with students, faculty, staff, and all that I'm doing today, all that I'm doing today is the result of teamwork. And in particular, I want to acknowledge my parents for the role that they played. I do this intentionally because I was lucky to be born a father that was an engineer and a mother that was an engineer. And the outcome of what they did is what we will see next week. Can you hear me? Okay. So as an academic, one of the things that's always intrigued me, the why is it that Ghana in 1960 was at the same level of development as South Korea and Taiwan? What is that difference that led to them developing much more than for Nigeria? And it turns out that most of them recognize the critical role of technology and innovation as the primary drivers of economic growth. But they also recognize the importance of economic development, recognize the importance of science, technology, and innovation. But the importance of research was not equal. And so I'm going to give you examples today that show that the scientific countries that invest in science, technology, and innovation, especially in research, that's what most discovery. In the end development, if they have a critical mass of people in the country, and they basically have 1,000 scientists and engineers and everyone. Now, as I began to look at this, the question that I asked myself was, is there a model that can bring African scientists in the diaspora to work with African scientists in the area, with students, with faculty, with international collaborators that come and join us again, in a way that allow us to be a major part of this scientific approach. So the question I asked myself was, why not Africa? And unfortunately, why not Ghana? So next slide. Next slide. So typically when major development happens, it happens around the Industrial Revolution. So the first Industrial Revolution, this was a revolution that brought cast iron, it was a revolution that brought textile technologies. And those that got involved in that era developed and became wealthy. The second Industrial Revolution was the era of automation. And during this era, those that got involved in automation and manufacturing like Ford changed the world. And they created a society that was thriving. The third revolution was the revolution of information technology, the revolution of computing. And those that got involved created great wealth. So now we have the fourth industrial revolution, the era of the information technology and transition enabled by AI. And then the question that I have is, can we afford not to be a part of this revolution? Next slide. So if you look at this next slide. What you see there is a simulation of an autonomous vehicle moving through the road, and we have better sensors at the time. That car can detect obstacles and avoid them. It can be traffic lights, and the vehicle itself in a safe way through this kind of activity. All of this is enabled, of course, by Sunyani artificial intelligence, which is widely available in terms of its impact in many applications. So, if you look at these opportunities range from technologies such as communications to art, where you use the idea of basic new artistic renditions of your design. Next page. Go back. It also raises the recognition when you use the AI approach to allow us to embed African languages and language models and translations of different kinds within this era. Next. So for me, I decided to give you 3 examples for how this kind of technology can manifest. I'm just giving one example that comes from the world of breast cancer. And the question is, can we use AI approaches to enable the early detection of breast cancer? And I'm going to give you a second example that comes from making the solar cell batteries of today and tomorrow. And then I'll give you a third example that will Calendar, and Calendar will speak about how to design the material for tomorrow. Next. Now, the pictures will show this because there was an era in this Africa was so in the area of Robotics, we had many drones and local materials, and they were so successful at this that they really become some we have the chance to go and go down. But then afterwards, we started innovating for the last few years. And the question is, we get back to the beginning by designing the next generation materials. Using the opportunities of artificial intelligence and machine learning, and people like all of us here in this community that would like to see this happen. So what I'm going to do is I'm going to give you examples of how we can design those materials, show you the work done by other Africans that have enabled this. I'm also going to show you cancer detection work, as well as work on renewable energy. Next, please. Okay, so in this case of solar cells, I'll talk about perovskite solar cells, which are solar cells that I hope one day we can manufacture right here in Africa. I'll also talk about different approaches to detecting cancer that can be translated into activities right here. Next. So let's start with solar cells. The basic idea of photovoltaics was invented in 1839 by Edmond Becquer, and the key idea that led to the solar cells was developed by Albert Einstein in the photoelectric effect. So with that kind of physics and the development of silicon as a material, next please, we ended up with a situation where silicon solar cells are ubiquitous across the earth. But the problem is that it costs you at least $100 million to build a silicon solar plant. So the question is, can we grow this organically from the lab to reality? And the most recent development of perovskite materials means that you can solution grow the solar cells in a way that can be done outside of a clean room. And so, in looking at this, next please, what we now have is the opportunity to make perovskite solar cells that have better efficiencies than silicon solar cells, but you can grow them in an environment that is not a clean room, in a way that allows us to have the opportunity to innovate. Next please. Now, earlier on, I had been involved in work to make organic light emitting devices. And so what we found in that work is that if you apply pressure to the devices, then you have the opportunity to increase the contacts at the interfaces of those devices in ways that improve their performance. Can you hear me? Oh my God. Okay, let's start again. Can you hear me now? Okay. Thank you, Dabiri. So earlier on, I had been involved in work where we wanted to make light-emitting devices. And the way we did it was to apply pressure to those devices during the fabrication. And out of that came a pattern for applying pressure to light sources in pixels of your television that was licensed by Samsung. So I then said to myself, why not take this idea of applying pressure and apply it to solar cells and batteries and see if we can improve the performances of those devices, just like we did with the LED devices. So when you do that, what you find is that you are basically applying pressure to a device, and as we increase the contacts between the interface, the ion transport and fast transport increases in a way that improves the performance of the device. So this is how this works next week. We then look at architectures for solar cells of the perovskite. And the key idea was to apply pressure to the devices in ways that improve their performance, in ways that allow us to have more contact with the So as you increase the pressure on these devices, your power conversion efficiency is increased. And with this simple idea, we were able to achieve efficiencies of 22.5%, which is comparable to some of the highest levels of efficiencies in these devices. But as we increase beyond the setting pressure of about 7 megapascals, these devices started getting damaged or started to fail. So we decided to do some modeling work to simulate the contacts and the interfaces next phase. And as we did that work, we were able to understand from a fundamental way how the applied pressures increase the contacts next phase. We also did some computational work where we started to compute the contacts for soft impurities or hard impurities in ways that allowed us to design the product. Next week. So with this kind of work, we gain a lot of insight that is relevant to how we practically make the source. Next week. And you also, as a materials person, you start discovering that as you apply pressure, the phases in the materials change, and those phase changes also contribute to the relation. Next week. Then the next question is, how long will the solar cell last? So we did studies that show that as you increase pressure, you also have significant extensions in the lifetime of the devices. Next week. So what can AI do for us? So it turns out that when you look at those structures, they contain defects. And we can digitize the images of these defects, which are voids, cracks, porosity of different kinds, and basically do machine vision on these kinds of different sensors. And so basically machine vision methods and convolution neural networks, we can then learn the different states that are associated with different types of performance vectors. And you can begin to predict those defect states as functions of lifetime of the devices in ways that help you understand what really controls the performance of the device and what really we can tune to make better devices. Next thing. So for this initial part, we were able to relate the device performance, the defects, and we were able to gain some initial understanding of how to improve the devices. Then I went to our next stage to say, what if we, our team that includes actually a number of Ghanaians, a number of people from the US, want to make the world's leading solar cell? How can we use machine learning? How can we use these kinds of AI methods to develop? So we came Ghanaian into our group, a guy called Elvis Shumasi. And Elvis basically had the idea of looking at a global database that contains all of the data that has been published in this area. And so by doing that, he was able to identify a model that is able to predict the behavior of all of these solar cells that have been studied. Next week. He also worked in our team to tune the data in a way that enabled us to get the best possible results and outcomes from our efforts. Next week. So here I am, I'm showing you data from about 10,000 devices, which is a reduced population from a database with about 40,000 devices that have been studied. And what this data shows is if you compare the predictions on the y-axis to the actual experimental measurements, essentially the data that falls on the 45-degree line is data for which the predicted data predicts the experimental data. And what we identified was a random forest model that gives the best prediction of the power conversion efficiencies of these different compositions. And so with this kind of work, you are able to identify how variations in the compositions of the devices really alter the efficiencies, and you can actually predict situations where you can get better devices that are ever been made. Next please. We could also show that the random forest model has the lowest error in a way that basically allows you to identify the predictability and the errors associated with your approach. Next please. So the next thing was then to say, what is the sensitivity of these predictions to the different layers in the solar cell? And how can we use this information to make materials that have world record efficiencies? And so with methods like this, we're able to identify the best conditions for making those solar cells of tomorrow. Next please. You can also apply pressure and show that the application of pressure improves the performance of those devices. Next please. Now, so why does this matter? So if we could make a solar cell with an efficiency of 10%, that solar cell with an efficiency of 10% can power the whole of the United States if it's deployed on 22,000 square miles of solar energy. What that basically means is that sort of area of solar cell coverage can certainly power more than that. The other thing about this is with these kinds of solar cells that we can sail from the lab sphere up to applications, it enables us to make solar powered lighting of various types in ways that we can make our phone. Now, the solar lantern is the one that I showed there. That lantern basically costs enough so that somebody with an income of $1 per day can afford to use it. So the goal therefore is to build this kind of system and to couple them with batteries. Next please. So in the case of batteries, most of you have heard of lithium-ion batteries, right? So lithium-ion batteries are a new generation of batteries where there is tremendous potential to store energy within these lithium batteries in ways that we can enable through recycling, in ways that we can enable through innovation. The big challenge with lithium-ion batteries is that they are flammable, especially when you use liquid electrolytes. So we've been exploring the development of solid-state or solid-state lithium-ion batteries. Next please. So with those batteries, if we again explore this idea of pressure application, what you can show is that there are induced strain distributions of those batteries that can lead to failure with the application of pressure. Next please. And as we develop that understanding, we can run simulations of the batteries in ways that help us to understand the limits of those strains and how they might lead to failure. Next please. So with this kind of method, we can now see that as I increase my pressure application and use tracking, and so I know the limits to which I can apply pressure to get improved performance. Next. And so with those studies, again, we can identify the battery architectures that enable you to store the most charge, and you can then begin to think about the battery composition using machine learning and artificial intelligence. So with these kinds of approaches, we basically developed better ways of making all solid-state batteries, and we're looking seriously at opportunities to transition them into the scale in which they can go from coin cell batteries to pouch cell batteries and other batteries for other applications. Next please. And so our goal in this area is to improve those battery compositions using AI and available databases as you see here. And next please. And ultimately the goal, next please, is to make batteries for cars and bigger batteries for houses. So this is the kind of work that people like Abdullah and myself are doing here at Sunyani. And we would very much really like to see a group of people working in this area in collaboration with us. Now, if you look at these batteries, they are critical for electronic vehicles, but they are also potentially critical for gigabatteries with increased energy storage. Next please. I want to move on now and talk about breast cancer. So in the case of breast cancer, this is the second leading killer of women behind cardiovascular disease. And it accounts for 30% of all cancers in women. So the big issue in breast cancer is early detection and also the severity of the treatment. Next please. So here are some of the methods that are used to detect breast cancer. And all of them have their merits and demerits. The biggest problem is that most of those approaches are not easy to access in Africa. Next please. So we decided to explore a few methods. The first of these methods is to take a little drop of blood using a syringe aspirator. So when you look at those blood cells under a microscope, those blood cells have different curvatures, they have different fractal numbers, they have different complexity of complexity that you can analyze using optical imaging. So with those kinds of methods, what we are able to do is to apply AI to learn the features that reveal the presence of the tumor. And so with this database called the responsive database that contains thousands and thousands of data that's been collected over time. Next please. So by doing machine learning on that database, we're able to predict within 97% of accuracy the occurrence of breast cancer from those simple images obtained from taking a drop of blood from the person. Next please. You can now also go one step further and ask yourself the question, what if you do immunohistochemical analysis of tissue? So what that means is they go in, they extract the tissue, and from the extracted tissue, you can now stain to reveal different things. Now, when you look at those images, what you essentially find is that there are different levels of resolution in the images that have been studied. So the idea that we came up with was to have images of multiple resolutions that are analyzed in a way that allows us during deep learning to be able to predict or detect cancer with 99.9% accuracy. Next please. So here we're showing you some of the models that were considered. Next please. And we're showing you that this type of deep multi-resolution images gives you the opportunity to detect the cancer with a high level of accuracy. Next please. Now the question there is, how do we extend this into an African setting? And what does it tell us about cancer in Africa? So what we've been doing is working with people at the National Hospital in Africa, looking at cancer tissues extracted from women at different stages of breast cancer. Next. When you look at those images, what you see is that as the cancers progress from the normal state, the structure of the tissue gets disrupted, and there are clear evidence, even from optical imaging, that show that the tumor is evolving from grade 1 to grade 2 to grade 3. Next. In addition to those visible images, it turns out that most African women, when they get breast cancer, they do not overexpress the receptors that are overexpressed in most Caucasian women. Most Caucasian women express HER2 receptors, most African women do not. And so what happens in most African women is something known as triple negative breast cancer. So triple negative breast cancer is one that needs a different kind of receptor to target. And so in our studies, we found that those cancers in African women express receptors for something known as LHRH, luteinizing hormone releasing hormone. So if you look at the grade 1 cancer relative to the normal, you see the blue staining and the green staining. Those stains increase as you go from grade 1 to grade 2 to grade 3. Which means instead of using the normal HER2 targets, we can now use the LHRH target, the target of cancers, as we design drugs and as we design nanotechnology to detect the cancers. Next. So with these methods, we've been designing nanoparticles that are conjugated to target those LHRH receptors. And when they target those LHRH receptors, they enable the imaging of breast tumors to be done with high fidelity. And they also enable us to distinguish very clearly in the contrast between breast tumor tissue and normal tumor tissue. Next, please. What's even more important is, if I look at the drugs that we have tested, we've tested 2 drugs. One is called paclitaxel, and the other drug is called polyglutamine. If we target the LHRH, what that does is allows you to inject the drug into the body. It goes around the whole body and it attaches selectively to the region, to the breast tumor. And so with that kind of an approach, if you actually inject these drugs with the target into mice that we reduce the tumor in, you find that you shrink the tumor in blue or green down to the size of 0 in 2 weeks. Whereas if you don't use the targeted drug, the tumors grow and eventually the patient dies. So with these kinds of methods, what we're now doing is proposing what is more personalized medicine, where you target receptors that are prevalent, you understand those receptors and their biological structures, and you now start developing new drugs that target or treat the cancer. Next. In the last part of the talk, I'm going to talk a little bit about how you make the materials of the future. So it turns out that designing new alloys especially, it is almost like cooking. So what do I mean by that? So imagine when you make a bowl of soup and you add a pinch of salt. The pinch of salt is like the alloy element that we have that totally changes the properties of the material. But it's a relatively dilute solution. So basically most of the materials we use are dilute solutions. What that means is, if I now have a 3-element alloy and I use equal proportions of each element, I now enter into a mixture space that's different from what has been looked at by most people. If I have a 5-element alloy with equal proportions, I start making what are known as high-entropy materials. So what we wanted to do was to understand these materials because they have the potential to be 4 times stronger than the existing ones. And we also wanted to regain a time in our history when Ghana was the top of alloy development with the people of the Ashanti, right? So we brought in the Ghanaian to our lab. This Ghanaian, I don't know what part of Ghana it's from, has done more for us in 2 months than we've been able to do for ourselves in a few years. And what I'm going to do is I'm going to show you the hard way of doing this, and I'm going to show you the easy way of doing this with the Ghanaian. So the hard way of doing this is to do computation. Next. So to do computation, what you recognize is that there are strengthening models that are associated with different defects in materials. Those can be point defects line defects, surface defects, and volume defects. If we assume that we can superimpose all of these vectoring mechanisms, then we can do the hard work of trying to write out the distribution models that give you that full spectrum. So what that looks like, go ahead, is something where you can develop full models and you can begin to try to test those models using structures known as microfillers. Next. So microfiller is something that looks like this, where you make a micron scale pillar that you can deform in a microscope. Next, when you deform it, you get defects that form and start multiplying into the discrete. These are called dislocations. And as you continue to deform, please keep going. You get more defects which start interacting. Please keep going. And those defects have been interacting right to spectrum. So, please keep going. And also now say, I want to simulate that in a computer. And when I simulate that in a computer, I can begin to better understand how those defects interact and they contribute to strength. Right? And I can do this up to some certain scale. Next please. And out of all that, I can then predict the stress-strain behavior of the material in a way that consumes tremendous amount of computational time. Next please. And if I want to simulate actual dislocation densities with a well-deformed structure, I have hundreds of millions of these defects to account for. And here is a simulation of those and how they give rise to the strength of the material. Next please. So out of this, I can predict the stress-strain behavior of these materials at different scales. But it takes a tremendous amount of computational power to do the prediction. Next please. And in the real case, where I get to the highest structures, this can be very complicated. Next. So let's look at a different way using machine learning. And this is the work of Sunyani. So what we can say here is there are about 18 different elements that are used in all of the high entropy materials that have been made. And we can go into a global database and do machine learning on that data and use that to predict the basic mechanical properties, strength, ductility, hardness, the basic mechanical properties. So with this kind of an approach, we can now look at the data for 4,500 hours and we can see if we can develop within us new materials with world record properties. Next please. So here is the result of 1 month of work for Sunyani. So what it basically shows is that we can predict the ductility of all of those materials. We can predict the Young's moduli. Next please. And we can also predict the densities and hardness values. Next please. And we can predict the yield and ultimate strength. Now when you look at this, it doesn't reveal to you what it reveals to you. So most materials have strengths of about 1,000 megapascals. I have materials on that have strengths of 2,500. And I asked Elvis to take out the data for materials that have strengths of 4,000 megapascals. What that basically means is with computation and with machine learning, we can sit here in Sunyani or in any part of Ghana and do models like this to identify compositions that have never been explored before. We can also begin to think about how we connect those ideas to manufacturing in ways that can scale from our own environment. Next please. Next please. You can think also of taking scrap. So you can take scrap material from stainless steel, you can take scrap material from cobalt, you can to start mixing them up and guiding the mixture properties of those tracks in ways that allow you to give value to them. And here's the result of Desmond Clement, who's another Ghanaian who has done this kind of work. Next week. So what I hope I told you is that if you do this kind of work, we have the opportunity to use theory works for us, we have the opportunity to use material, we can use it in problems of health, we can use it in problems of energy, we can use it in problems to develop new alloys. And as we do all of this, it opens up the opportunity for us to start thinking about how we make things. Next. So here's my challenge to all of you. So this is a picture of the materials of Africa. So what you see there is that Africa contains about 1/3 of all the Earth's raw materials. 1/3 of all the Earth's raw materials. But the only African until now that has been able to figure out how to give value to this is Dangote. So Dangote has exploited only one silicon deposit for cement. Right? So the real opportunity is how to get the next generation to really think about how we can add value to all of these elements that exist within the earth and recycle them in ways that can be enabled by manufacturing. Next please. Now, if you start thinking like this, you should also realize that there are new ways of manufacturing that are digital. And those new ways of manufacturing that are digital involve using lasers to guide the digital writing of structures to make components. So those kinds of methods are often additive manufacturing methods, using lasers to do laser additive manufacturing. And there are opportunities for us to think about how do we engage with places such as Sunyani as part of how we teach the students and how we do research in materials and manufacturing. Next year. We can also start rethinking how we do manufacturing. Because what we can do is create the interface between the robot and the human as part of our strategy for manufacturing. Because if you look, for example, at SUNY Polytechnic, we have 2 semiconductor factories on our campus. In those 2 semiconductor companies, what they do is robotically assisted manufacturing. And you find that the natural interface between the scientists and the engineers and the technicians and the shop floor is always mediated by robots that make those processes efficient and also create the 21st century workforce that we can all aspire to. There are also people these days who are looking at robots that assist in construction and robots that also can assist with agriculture. So if you look at the top left, what you see there is the robotic tractor. The robotic tractor was developed by one of my students, Kenan Banesi, where instead of the usual tractor that we all use that's heavy and difficult and clunky, here's a robotic tractor in a base that can plant, that can harvest. And what I always think in my mind is we should make the food processing and packaging structure next to this in a way that will integrate the robotic tractor with the robotic packaging system. Next to it. By the way, for those of you that are entrepreneurial, what we would love to see would be projects that connect students from SUNY Polytechnic with Sunyani Technical University, where you incubate some of these new businesses in a container. I show this in a way to try to challenge you, because a lot of times you say, oh no, this is too big. But what I show here is something that will take our knowledge in materials, our knowledge in robotics, and knowledge in manufacturing, and bring it into ideas like this that can be created on the campus of the university in ways that can give value to these ideas. Next slide. So in conclusion, what I try to show you are some next frontiers in materials, in manufacturing, and in robotics. I hope that these do not seem to be something that is different, but I hope that for you, these seem to you are things that are possible. I gave those examples to show that you don't have to have much to think about doing research. There are often people who say, I don't have this equipment, I don't have this, I don't have that. But I always maintain that as long as we can think, as long as we can write down ideas and collaborate, there are ways of overcoming those challenges in ways that allow us to go from theory to experiments, to machine learning, and collaborations that make the transition to reality possible. I try to give you some examples of solar cell, examples of breast cancer detection, and also examples of design in our. By the way, in all of those areas, there are Africans doing that work, working with folks from the United States, working collaboratively in ways that give value to those ideas, in ways that can be enabled through the collaboration of the Vice Chancellor and negotiator, the SUNY Polytechnic, the ways that we can work. And I hope that you will be excited enough to consider these ideas as part of our collaboration and to be inspired by the Asians before us. I always say, in some senses, we were part of the Asians in 1960. Today, during this era of the Fourth Industrial Revolution, I urge each and every one of you to think about how we can work together to leverage today's opportunity to really work towards this era of the Fourth Industrial Revolution, to use AI as engines for African development. And like the Asians before us, I look forward to a new generation of African lions. Thank you very much.
Let's give up for you can do better. Let's give up for you can do better. You can do better. An insightful and impactful presentation from Prof. So, without wasting my time, we are going to open the floor to take your questions. Please be brief about your questions so we can accommodate your questions. So we are taking 5 questions from staff, from students. Don't feel shy. Whatever question you have, please raise your hand. I will count them and then take your question. Staff, please, you are included. So if you have a question for them, don't be afraid to answer the question.
Thank you very much, Prof. My question is, if I pick any model without making any changes to the model and I test it on any data set, has there been any research? Any existing model like convolution neural network backpropagation, I test it on data from maybe Tata. My question is, has there been any research? And I'm able to predict 90%, 97% to confirm the work that I have done. Because what I know is that research should contribute to existing knowledge. And now I'm picking existing algorithm to just test the data. Has there been any research? Thank you.
Yes, I think that's what I was trying to show you. So what we do is, let's say you have a data set that has 100% of the data with 50,000 data. What we do is we use 75% of this in training the model. We use 75% of this in training the model. And then the remaining 25% of the data we use for validation of the model. Okay, and the message of this talk really says that when we have those kind of established data sets, by dividing them up, we can not just show not just train the data set, but we can use part of the data set to validate the model. And so, in that sense, I think with this kind of an approach, we can do more or less what you are suggesting, provided we partition the data to validation data versus training data, right? Now, the question that one can then ask is, how do we make sure that that data is relevant to Africa, in other words, basically training user people in responsible. And then what we suggest to do is we train with increasing data that we start to obtain from Africa to modify that initial predictive status. And we also use transfer learning to enable that transition to happen. Is that not the question you asked? Please, I don't understand. Try it.
Hello. Thank you, Prof. Actually into, I want to ask a question on advanced manufacturing. In your presentation, you made mention of using advanced manufacturing technology to produce products, and then you were of the view that if you have an idea or you want to undertake research into advanced manufacturing, it's not all about the logistics being available. But I'm also of the view that if you have an idea, and that idea is, for example, an individual research, but not, let's say, a PhD research that you are doing, how are you going to collaborate with somebody outside of Ghana who has the necessary or lab, which has the necessary resources to be able to do such a research? Because, for example, laser technology is one of the advanced technology that is used in manufacturing. This part of our world, we don't have that. If I am a researcher, let's say a lecturer, which I've gone through all my training, and I want to conduct an individual research, not a PhD program, how will I collaborate with a lab outside Ghana to be able to perform such a research?
Thank you, that's a good question. So in that case, I think the important approach is to network. So for example, in our case, we do not yet have the metal printer. So what we do is we collaborate and network with groups in South Africa where they have that kind of system to do 3D printing of metal. And we also collaborate with another group. And if you are, for example, interested in that kind of thing, what we are proposing with SEPA is a networking opportunity where we connect to those people who have those resources. And so the key advantage of being in a network is that you don't have to have all of those resources to do the work. You can work within the network to find people that will help you get things done, so that you don't have to necessarily have that equivalent. The other piece of this is we have some funds for mobility of faculty. And so part of what we're discussing in the exchange is to have a situation where there is funding for people to go out for 3 months, 1 month, to do work in different areas, potentially for up to a year as part of postdoctoral research. So I think that this in pragmatic ways, there are ways that we can use the collaboration between our universities to facilitate the network to allow you to do this. Any more questions?
Okay, thank you, Prof. Please, my question is about computing power. AI needs a lot of computing power to work. And in Africa, we are lagging behind in terms of computing power. So I want to know, back in the US, what are some of the things that schools are doing to help students in terms of computing power? But just this Monday, I gave students some semester project work to do to build a chatbot using Hugging-Face transformer. And they were not able to do it because it required, like the data set was about 18 gig and their machine was not able to handle. And supposed to call up to, they will have to pay, and none of them had a credit card. So I want to know what are some of the things that have been put in place in the US, say by the institution, to help students with some of these computing issues. Thank you.
It's a good question. So one of the things that we are doing is we have access to supercomputers, and depending on the way we structure collaborations, those that we work with can have access to that kind of structure. But we also have access to workstations that you can access remotely. And so part of the thinking is, depending on the types of problems that we're trying to solve, we can facilitate access to workstations that you can access, but we can also facilitate, as a program, access to supercomputing. And of course, if you think about it, you can keep things as well in the cloud. So I think it's really how we pragmatically work together to overcome these challenges and provide access for each other. So one of the things that I would like to see us test is how to get some computational work that is going on here connected to those resources in a way that will allow us to solve some important problems together. So let's maybe talk after this presentation. And if you want to also, please make sure you reach out to February and to make sure that we maybe try one or two test programs. Yes.
Thank you for your presentation. Listening to you, it seems to me that without the background in medicine, oncology, or radiology, engineers can, for instance, go into breast cancer treatment and breast cancer care. Is that the impression? Are we there yet?
You know, the most important thing is to collaborate and to be willing to learn. So, in my case, for many reasons, I was motivated to really do something with the breast cancer. But what I found was that it was important to talk to medical doctors, find out what is your real problem, talk to oncologists, find out what are the limits, and the key thing here is to form a team of collaborators, where you actually find that you can bring your own skills into the problem. And then as you begin to collaborate, what you then realize is that you learn from them, they learn from you, and you can do something unique because of your combined background. So you don't have to be an oncologist to do the kind of work that you do. You have to bring something in. Sometimes it's computational, sometimes it's experimental, sometimes it's machine learning. Depending on what you bring and the problem that you're trying to solve, it is that interdisciplinary collaboration that is important, and that is what enables you to solve the problem.
All right, Prof, thank you. When it comes to these deep learning, machine learning, and other things,
You see, when we talk of deploying it on a computer, we don't have problem with computational power because there are these NVIDIA products like GPU and the rest. But then looking at this material engineering, which is, I think that is your field, you see, we are interested in deploying these things in robotics or robotic systems. So in your research, do you consider things like energy consumption, memory footprints, then maybe the computational power of all inference speed at which the deep learning is going to run on such devices? I want to know. Thank you.
I think the people who run the models consider this. To be honest, my perspective on this is more from the materials design approach, where I'm thinking about essentially the computational capabilities to handle the number of different variables and the number of different processes I'm trying to simulate. But there are others, of course, who consider the power consumption, especially in places where you have large-scale computation going on at a very, very high level. So this is, again, part of, in my mind, this is the problem that I would like us to have. I would like us to have a problem where the rooms are so hot that we have to have the right cooling systems, the right thermal management due to the volume of computation that we don't have that situation now. But I appreciate that in the places where that happens, this is part of what you need to run a data center or something with a very high level of computation. This is not where we are. Thank you. Any more questions? Thank you.
All right, so our faculty staff, give it up for you, our faculty staff of engineering faculty, those who have more technical and detailed questions. Our guests are still with us right after the program. We can see them and then interact with them. All right, so without wasting more time, we'll call on the highest office of our university to give us a very short remarks of the whole. Let's give it up for our Vice Chancellor, Engineer Professor Soboyejo. Let's give it up.
Good afternoon to you all. I hope you are fine. The presentation is so powerful. If you are not careful, it begins to motivate your mind. But I think that is why we are here. As engineers, as technologists, as scientists, this is what we have. And you are here as students to learn and go out there and create new materials, create new chemicals, create new medicines for the world to use. Good. We are happy to have our partners here from SUNY PI, all the way from Utica, New York. And they have done so well this morning. We had a first session with management, and there were a lot of things that we discussed. The bottom line of this collaboration is that, as you have seen Professor Soboyejo presenting a lecture here at STU, it tells you that it is possible for some of our lectures we also move all the way to the US to give presentations. That is the kind of things Prof was emphasizing on. This is partnership between the two institutions. We signed an MOU in the year 2023, and we started the implementation process. And what we have seen today is part of it. You can also see very soon that students from SUNY PI will visit Sunyani Technical University for exchange programs. And in the same manner, our students will also visit New York for exchange programs. So really glad to that. And Prof emphasized on collaborative research. Our lecturers, I think some of you have questions, very beautiful and difficult questions to do. The partnership has just started. Just as Prof mentioned, Sabri Asumadu, who is one of us, is a lecturer. Sabri, where are you? Can you stand up for us to see you? He is a lecturer at the Materials Engineering Department of Sunyani Technical University, and he was actually doing his PhD here in Ghana. But he got to a point where he found it very difficult to complete the PhD research. So we had to maneuver and find out opportunities out there for him to go out there to complete the research. And that is why he finds himself at the SUNY Polytechnic. But he is actually one of our lecturers at the Sunyani Technical University. So it tells you that this is the kind of opportunity that avails any lecturer, any student, when you complete and you want to go and continue your education, you can have the opportunity to enter this university. That is SUNY PI, that is State University of New York Polytechnic Institute. You can easily enter there through the collaboration. That is, if you go through the needful processes and steps. So it is an opportunity for all of us. Let's grab it and let's be ready to explore all the windows within the collaboration or partnership arrangements that we have between our two institutions. So, Prof, thank you very much. We are very grateful to you and your team for coming all the way to Sunyani Technical University. In 2023, some of our staff visited SUNY here, led by the Dean of Faculty of Engineering. So now that they have come, it is our turn to go. So next time when we are going, I am sure some students will also have to follow. Building up to that one as well. So the links are there. We will link Sabri Asumedu will have to be available to you, especially the lecturers, so that you can pass. It's about collaboration. It is not every equipment that we can have, even in the whole country, in Ghana. But once they have the database of our collaborators, we can easily, let you be attached to a group which can easily assist you to complete your work. So on this note, we say that we appreciate their coming and we are very grateful to all the research that went into the presentation. I could see a lot of calculations. When you look at, when I remember my sixth form chemistry, and I could see copper and chromium and all the other elements, and you see where the research is going, putting them together, about 3, 4, 5 materials together, and then Prof was talking about the strength going into 3,000, 4,000. Still we as civil engineers, we know that the strength of steel is either 250 or 400. So if we are getting new materials that are so strong, it means it will help the construction industry and other industries as well. So on this note, thank you very much for coming, and we appreciate your attendance at this important occasion. Thank you.
We can do better. Let's give it out for Prof.
Please, we can do better. Let us do better. If you know that AI is going to change your life, you can do better. Thank you so much for your time, your attention, and your patience. We've gotten to the peak or the highlight of our program, which is our gifts and award that the school has for the SUNY Polytechnic in the USA. Faculty team members, you are so special to us. Honestly speaking, you being here today, we appreciate it, and no gifts can ever repay you. So take this as a token of our appreciation. Without much time being spent, I invite Dr. Asunodetabri to kindly come forward. Please clap for him. He is one of our own spearheaded this unique program. Professor Odo, please join me to do this presentation on behalf of Sunyani Technical University. Please let's clap. Yes. If you can't speak in front, please clap. At least that's the least you can do. These are the celebrities of our time. Yes, you should be taking good pictures of them. Thank you so much.
Let's give it out for him, please. Our very own.
Please, let's keep the applause coming. Let's Thank you so much. Next on our list, we have Mr. Willie Johnson. And the presentation will be done by Professor Samuel Biafre, the Dean of the Faculty of Engineering. Let's keep clapping. Yes. As we just get going, thank you.
We are
inviting Dr. William Johnson. The presentation will be done by the Director of Finance, Mr. Thomas Prof. Let's have a show. Please clap. The teacher alone is given. Let us clap for this one. This is our partner.
You can do better. Let's give it out for him. Let's give it out.
Next on my list, I have Dr. Stephen Schneider. Doctor is being given a gift from Dr. Peter Hansen. If you are
Dr. Peter Hansen is the International Relations Director.
the man of the woman. And if we were to be in the kingdom, the king himself is going to lead us in the person of Professor Engineer Kwadwo Edinkra Appiah to give the presentation of the gift to Professor Wole. Please let's keep clapping. Not excellent. Not excellent. One can mistake something is just too much. We have the praise. Africa must rethink, we must think, we must supply expectation, and we must do our best. Keep clapping. I do not want to hear the room is silent. Thank you so much, sir.
Thank you very much, Prof. So, earlier before we enter, someone was asking me, is SUNY University, STU University, USA? Yes. That is our branch in USA. SUNY University, Sunyani Technical University. Give it up.
So, some few knowledge nuggets for this outstanding event. AI is transcending all fields of our life. You can choose to be part or choose to show your head in the sun. Today, if you are in this room with me, I believe that Africa has something to offer. We have intelligence, we have grit, we have knowledge, we have determination, and we have diligence. As we bring the curtains down to this program, I want you to leave with these few words. We can ensure that we have varied energy, diverse energy, reliable solar power with AI. We can assure that no woman dies from breast cancer. And we can only make sure that comes to pass if faculty members from both universities are willing to work together. Today's program has been outstanding. Thank you for your presence. Thank you for your beauty. Thank you for your participation. We are closing with a prayer from our very own University Chaplain, Reverend Vivian.
Before we take our closing prayer, faculty members, heads of unit, heads of departments, your presence is duly acknowledged. Thank you very much for coming. Tomorrow is the second lecture series, so please, tomorrow all students and staff, you are supposed to come. Know that we have our final lecture series for the day. Reverend, please give us a closing prayer.
Thank you, shall we pray? Father, we want to once again thank you for this wonderful section that we have. We thank you for the life of Prof who has shared this great knowledge with us. But what we want is that this knowledge will find expression in our works. So we ask for the impetus to be able to appropriate it effectively for the benefit of our society. Be with us for the rest of the day, wherever we go, your hands will rest upon us and shall preserve us. Now unto him I commit you, that he shall preserve thee, watch over your soul, and give you peace, now and forevermore. Amen.
All right, so there will be a photograph with me, so students please wait. So we are taking an official photograph with our team. Prof, please, we'll be there at here. Right after that, staff, faculty members, and then the team, then students. So tomorrow's program is starting at 9. All HODs, letters have been called. So all engineering students, tomorrow at 9, we are expecting all of you here at the auditorium. Students should wait behind. We are going to take a photograph with you. Please join us. All right, now some can take leave of us and students please join us here. Prof, can take the student please. All students are welcome will come. Next year you see yourself in Canada. Thank you very much. See you all tomorrow right here.